Hello. For those of us who like using scikit-learn, there exists a library called skorch, which acts as a scikit-learn wrapper around pytorch. All you have to do is a pip install skorch. Here's my version, and you can start integrating with pytorch on your applications. For this demo, we're going to go through a regression notebook. So let's get started. Here are the package versions of pytorch 2.0.1, skorch, and sklearn. Those of you who have a version that's less than 1.2 won't have prediction error display, so please make sure that you have this package installed. Moving along, we set the seed for both CUDA and the manual seed as well. The device is set to CUDA, and I want to make sure that I train only on a CUDA device, so hence this assertion is there in place. Next, we have our scikit-learn datasets function. We call make regression. We want to make 200 samples, that is 200 rows. There are 2 input features per row and 1 target per row. PyTorch usually complains when you convert from NumPy to tensor and use it for training, because the weights are initialized to 32-bit values, and when you convert a NumPy array to a tensor, it becomes a 64-bit float. So just for consistency, I'm having both x and y as 32-bit floats. These are the shapes: 200, 2. 200 is the number of samples, 2 is the number of features. Same holds true for y. Y is the target variable. Then we use the train test split from scikit-learn again to do an 80-20 split of the data set. Here are the shapes. Moving along, let's look at the distribution of the features of x in the training set. We can see that feature 0 has a distribution of about between -4 and +2. Feature 1 is around -2 to +4, and they look kind of normal. Well, we won't be focusing on feature engineering at this in this demo. This is to make a choice of a scaler. We'll be using min-max scaler for scaling x features. Similarly, if we look at y, we have the range here, and I'll be using min-max scaler for y as well. Here's a helper function called print performance. This is used to provide the performance, rather the metric that we're interested in. So we have here a model that will get fit on the training set if it is not already fit. We have an optional scaler. If we provide one, we'll fit and transform and perform an inverse transform when required. The metric of interest is going to be mean absolute error. To get a baseline of our dataset performance, we'll use a dummy regressor. The default strategy here is mean, so for every input it will just predict the mean of x train. So when we go ahead and predict on x test, this is the L1 loss or the MAE. Similarly, when we use median, here's the MAE. When we use the 75th quantile, here's the MAE. As you can see, it's around 42.6-ish. Let's now move to the skorch part of the notebook. We have here a torch module. So this is an instance of a torch module. It's a sequential module containing 2 linear layers and a ReLU operation in between. This is the class that you want to make use of. So neural net regressor is a wrapper that does all the heavy lifting for us. Here we can either provide a class, that is you subclass nn.module and then you provide a class, or just the way I've done, you can provide an instance as well. The optimizer I'm going to use is Adam. Max epochs is going to be 200. I want the training to be done on GPU and hence the device specification. As far as the batch size goes, 32 is a reasonable pick for most problems. Although here they use a default batch size of 128. As far as the criterion is concerned, I'm using L1 loss here, the default being MSE. Turning our attention to the list of callbacks, we have one here called early stopping. Its purpose is to kill the training loop when validation loss doesn't improve beyond a certain level across successive epochs. So let's just look at how things work, and we'll get back to early stopping in a minute. So we have a pipeline here. For those of you coming from the scikit-learn world, they should be familiar. We use a min-max scaler for the input features, and then we use a neural network, that is this one. Then we have our fit train call. So here's the run. So across each epoch we have train loss and validation loss. These are the primary quantities of interest to me. So if you see something in green, then it's going down. If it's black, then the loss is going up. We prefer things going in green. So if we scroll all the way, we see that validation loss did not improve in the last 5 epochs, and the best model is restored from epoch 41, right? So for 5 epochs there was no improvement, and hence this early stopping kicked in. As far as early stopping is concerned, it's going to monitor validation loss. So those of you who are wondering, we just provided only X train and Y train. How did we get hold of a validation set? Internally, the regressor does another 80-20 split of X train. The data statistics are gathered across entire X train, but the training set, that is the model, is fit only on 80% of X train, and remaining 20% is used for validation. Now coming back to the threshold mode, right? So we have validation loss here as 0.7152 and 0.4886. Since the threshold mode is set as absolute or ABS, so the next one has to be strictly less than 0.7152. That is, lower is better. The loss as it goes down is better. So that's the way it progresses. However, if we had set it to rel or relative, which is the default value, then there is a slight calculation that goes on in figuring out what the next cutoff should be. So the way it's done is you take the score and multiply it by the threshold, which is 1e minus 4, and then the score minus this change is a new threshold. Got it? So that's how it moves forward. So there we go. We have our pipeline object here. As you can see here, we have an X scaler and then the neural network consisting of 3 layers. So to save our entire pipeline, right? We have to save both the pipeline and the Y scaler. So this is a test that just loads the saved pipeline and checks to see that the parameters are saved properly. So we check for X scaler, we check for Y scaler, and then the neural network. The name and value correspond to, name will have values like name, weights and bias. The value will be the tensors that correspond to the key. That's about it. So for those of us wondering how to make prediction on a single data point, data has to be batch followed by the number of features. So here we have a batch of 1, and then we have the number of features here. When we do a predict, since the model was trained on Y scale data, we have to perform an inverse transform to get back the data in the original domain. So this was the prediction and this is the actual value. So when we do a check on the test set, here we have very good performance of an MAE of 0.145. To visualize your error distribution, we have our Y true and then we have our Y pred. So here are the predicted values and this is the residuals, which seems really well distributed across 0. There are a few points where it is going a bit off, but the deviation seems to be fairly less in my opinion. Here is another plot you can use to view the distribution of errors. Seems fairly straight. The predicted and the actual values seem pretty close. So that's about it as far as this regression notebook is concerned.